Okay. Buongiorno, buonasera a tutti. Sono molto felice stasera di accogliere Silvan Oesterle, che è venuto da Zurigo per noi. Provo a farlo in italiano, quindi. La conferenza è organizzata nell'ambito del corso Integrate Digital Tools e con la collaborazione dell'Associazione dei Studenti. La conferenza è intitolata Designing Processes, che anche per gli studenti che fanno il corso è molto interessante come esempio di pensare non così tanto alla forma, ma veramente a ripensare con questi nuovi metodi digitali al design process, come si utilizza quel computer non come un strumento di rappresentazione, ma un strumento di veramente progettazione. Quindi è piuttosto sui processes, sui metodi di pensare nuovo, come si può generare un'altra architettura, un'architettura che si concentra su altre cose, non forse la forma, ma più sui processi come per esempio la costruzione o la generazione di una forma, utilizzando anche la programmazione come un strumento di veramente architettonico. Silvan Oesterle ha lavorato a Zurigo nel 2007, ha studiato anche a Stuttgart e dal 2007 adesso lavora anche alla ITH nella ricerca nell'ambito del digital, come si chiama? Architecture and Digital Fabrication dai professori Gramazio Kohler. Forse conoscete un po' le opere di Gramazio Kohler che hanno sviluppato nell'ambiente dell'ITH, per esempio il padiglione per la Biennale a Venezia, con quella che si chiamava Structural Oscillation, con quei mattoni che sono costruiti con il robot. Una parte robot. Si vedrà dopo. Una parte interessante anche come si può sviluppare dei nuovi strumenti per gli architetti, non soltanto utilizzare, non so, un laser cut o qualcosa del genere, ma veramente pensare come si può anche prendere per esempio un robot che viene dell'autoindustria per utilizzare quegli strumenti per fare dell'architettura. Si vede tanto, è molto interessante la nozione che l'architetto fa i suoi strumenti, e anche abbiamo fatto qui per esempio con quel prototipo con Leo e Francesco il 3D printer, che il concetto di questo piccolo 3D printer è anche che gli architetti costruiscono il loro printer e si riproduce e uno fa l'altro. Comunque Silvan ha anche il suo ufficio che si chiama ROC, Rittmann Oesterle Knaus, e lì provano anche a utilizzare nella pratica quegli strumenti come scripting, programming, con veramente dei progetti reali che fanno dei padiglioni, delle facciate, delle cose varie, per veramente provare di utilizzare queste cose in un ambiente reale. Io sono fortunato, abbiamo potuto fare un progetto insieme che non so se lo mostrerà stasera, ma è anche un amico mio adesso. Penso che veramente è un parte anche il futuro dell'architetto, non è il futuro dell'architetto, ma sarà una parte che sarà sempre di più importante nel nostro mestiere di architetto, di integrare queste medie digitali con gli altri media più tradizionali per sviluppare un'architettura forse nuova. Per finire voglio dire semplicemente ancora una volta che è veramente l'interessante è veramente il processo, come veramente si sviluppa con questi nuovi modi di programming e scripting, come si può sviluppare un pensiero, una logica che è un po' differente che la logica di rappresentazione con il computer. Quindi sì, prima di lasciare la parola voglio ancora ringraziare l'associazione degli studenti per l'organizzazione di quella conferenza e anche Francesco, che adesso non è qui, ma per la sua organizzazione e tutto. Grazie mille, lascio la parola.
Well, thanks, Jean-Lucien, for this very nice introduction. Unfortunately, I don't speak Italian, so I have to do the presentation in English. Well, many thanks for inviting me over here, and also many thanks to the Student Association who supports this event. I'll show today, as Jean-Lucien mentioned, research work from our office, as well as research work from ETH and office work that we do with our office ROC. The talk, as the title suggests, will focus on the reciprocal relationship between the design of construction and fabrication processes and the architectural artifact itself. So the talk is roughly structured along this diagram. It will start with projects that develop a construction or fabrication process and generate the architectural design through the application of the process. So towards the center of the diagram, we get more towards projects where the architectural and the architectural design process and the fabrication and construction process really become one thing. And towards the end of the diagram here on the right-hand side, we'll see a few projects where the fabrication and construction processes are adapted to the architectural design. So design is preconceived, and then the processes are made to make it buildable. So this is kind of the usual case that we find in today's building industry, and the left-hand projects are rather the case that we'll find in academia and education at the moment. And this might have been fairly abstract. So before I start, I would give you a quick idea of what developing construction processes for architectural design means for us, because although digital fabrication design is currently a prominent field in teaching and research at the most advanced architectural schools around the world at the moment, we think this is not at all a new invention. There have been numerous examples in history, and when we look back we find many important architects that understood their trade not only as an artistic discipline, but were also inventors of new construction techniques. I would even argue that the important architectural developments have always been rooted in technological shifts and their appropriation and later on into architecture. This is an idea that is greatly put forward in Mario Carpo's first book. I would strongly recommend reading his theories. A nice example that you can see here is the Renaissance architect Philibert Delorme, who is mostly known through for his designs for Château d'Année. But he was also a great inventor of new construction techniques for architecture. And he furthered his architectural designs through these inventions. So for example, at the time in France, wood was very limited. And it was not possible to get large wood elements to build large spans. So he developed a system that you can see here, which is similar to the reciprocal frame system, or similar to the Zollinger system, which has been developed later on.
The laser pointer.
It's fine. I'm good. Yeah, and he described a lot of his inventions. He wrote even books about all of his inventions. And this system then allowed him to build again larger spans and make more interesting or more important architectural results at his time through the development of that system. A more recent example is Pierre-Luigi Nervi's work. Here you can see Exhibition Hall B, where he used lost formwork concrete beam construction. So these elements you can see here, they are lost formwork into which the concrete is poured, and then they are left in place and become part of the structure. And they also become at the same time a very strong visual and an architectural element of these halls. And another example where the development of a fabrication process was used purely for the design aesthetic is Miguel Fisac's work from the 70s, where he developed a plaster mold with a flexible, so these panels were poured from plaster into a flexible fabric formwork mold with strings beneath the mold, so the fabric bulged into these strings, and these are these pockets you can then see here. So that is purely visual in that case, but he developed this design completely through the invention of a fabrication process. And when we talk about processes, it's also important to consider the tools with which these processes are made. And we think that a very deep understanding of the fabrication tool you apply is mandatory if you want to work with processes in the design of architecture or architectural artifacts. And a nice example for that are Japanese carpentry apprentices, who first have to develop their own tools for 1 year before they're allowed the first time to actually work on a workpiece. This is an example from Andrew Cuddles I stole from him. And today we think that as architects we not only have manufacturers or workmen on the site to our disposal, but we also have a huge array of all types of digital fabrication tools to our disposal. They're just usually hidden behind some obscure processes or submission system. But when we start going out into the industry and look around, we find many very interesting machines that we can either hack or appropriate to our needs. This is from a cutting knife, a wood sawmill that is digitally controlled, to robots, to 5-axis milling, to printing. There is a huge array, and it really does not matter what type of a machine, but that you need to appropriate this machine to your needs, and you can do that not by changing the machine itself, but by appropriating how you control the machine. And usually you control it via software, and that's why we also think that building your own software tools, not only for machining but also for designing, is a very crucial part. So we see the machines as a physical tool and the software, developing your own software tools as the carpentry apprentices develop their own tools for making woodwork. We think that we architects can develop our own software tools to make more interesting architecture. The first projects I would like to show are from the professorship at ETH for which I work. As Jean-Lucien mentioned, the Professorship for Architecture and Digital Fabrication, led by Professors Gramazio and Kohler. We are in the nice situation that we have a 6-axis robot to our disposal in our lab. And this machine is important for us because it allows us to do experiments on a 1-to-1 scale, which is crucial for the work at ETH. It can work in a building scale level, and we don't have to revert back to models. And this is important because the building scale elements have a certain weight to them. They have certain physical and material properties which are important to consider also while designing. The other important aspect of this machine is that you can exchange its hand. So what you can see here at the tip of the machine is completely exchangeable, and we usually develop our own tools for this machine. So we develop our own physical tools and our own software that controls the machine. And by doing so, we can implement a lot of different processes with this one single machine with which the students then can work, or we can do research with. The first project I want to start with is a fairly old project, one of the first projects ever made at the professorship. At that time, we were still students. And we were thinking at that time, what is the most kind of simple element which we could use the robot for? And we want to revert or use existing elements and not invent everything anew. So we're working with brick stacking, developed a specific gripping tool for the brick stacking. And the important aspect of this process is that you can place a brick in space with an absolute precision at any angle. And while developing the design, this became also the driving factor behind our intentions. So we didn't want to make deforming walls or whatever you could do, but we wanted only to work with modifying the angle of these bricks. And after testing what you can do with the bricks really in the physical realm first, we moved into scripting and then made kind of our own design setup. So this little snippet of code that you can see here was the complete design. And an important aspect, and that's why we favor scripting so much over tools like Grasshopper or mere modeling, we we enjoy the time boundness of scripting. So what you put here in the innermost part of your script comes first, and then what is here comes second, and so on. And this, when you work so directly with fabricating things, this is a very nice property, because fabricating stuff is also time-based. So you cannot place the uppermost brick first, but you first have to make the bottom layer, then the next layer. So this interior thing here is a layer. This repeats the layer to form a wall in the end. And this nice time-boundedness is not existing in pure geometry. So when you model these things, the machine will probably place a brick somewhere in the air, it just falls down. When you script it, you don't need any post-optimization after making your design. So you can test a lot. You just modify your script a little bit, you directly feed it into the machine. You can test your design on a one-to-one scale. And this then sparks new design ideas, generates new potential for the architectural design. So as I mentioned, we only work with the rotation of the bricks, use the traditional brick bond, and didn't want to transform the wall as to something that is not for what bricks were not initially intended. So brick walls, in our opinion, were straight, and that's why we only used rotation. But when you move along the wall, it gradually starts developing a three-dimensional deformation effect, which we really could only see when we were testing that on a one-to-one scale. And this was the final design. So the script you just saw and that wall, this is exactly what it was made from. We had the nice opportunity then after this project to use the system we developed for the winery in for the Gantenbein winery in Flash, a project by Andrea Di Platzis and the professorship I worked for. And there the system was adapted to work with images and was used for the facade of that building that needs a light filtering screen for the wine storage space. I already want to move on to the next project. This is a teaching project, the second one I taught at ETH. It's a 4 weeks research course, so a pretty limited time frame. And here we asked the students to work with an already developed fabrication process, design through that process, but in addition to that, think about performance requirements like constructive weather protection and insulation inside an exterior building wall. So they were asked to make building walls from stacking wood slats. The interesting aspect of this project is that the wood slats are a flexible module. You can cut them to length from 20 to 120 centimeters, which gives you a more interesting element to work with than with a fixed sized brick. And as you can see here, in this 4 weeks very short course, we really automate only what is absolutely crucial for the design. So cutting and nailing it is not an important aspect at that moment for the course, but the placement in the right position and location is what can change your design more drastically. And again, the first step in the semester is always to develop, to ask the students to develop their own design systems. So what is a design system? Under design system, we understand the kind of scope you can work within. So these models are nice examples of design systems. A certain arrangement of slats that in any case is producible. And then you can start modifying these elements by developing your own program tools. So you have a certain system. You can, for example, in that system, the students were able to modify the inclination of the slat and also the length of the slat. And within that system, every solution is producible later on. And now through, for example, the color of a pixel image, they can control these two parameters of the system. And this gives them the possibility to explore a huge range of variation and enhance your design, but also the performance of these walls. So this is in absolute contrast to what Greg Lynn coined as the happy accident, where you generate something in the computer, then you look at the outcome and you search for interesting aspects in the outcome. This is exactly the opposite. You make your system, within that system every solution will work, and then you can explore this wide variety of solutions and enhance your architectural results. So this group worked with the inclination and the length of the slat, and they were arranged. This is the outside of the building shell, so they were arranged that they shed the water away from the wall, which you can see here, and the face wood is always pointing down, so that there's no fungus infestation on the face wood, and then actually they had to work with all these limitations, so you could only cut the slats straight, no angles, and so on. And they did many tests with little mock-ups they were watering onto and fed them then back into the design and modified their design so that they can protect the structural parts that are behind these kind of sacrificial layer slats of the wall. You can see nicely here. This is the vertical load-bearing plate, which is straight in the back. This is the sacrificial layer that sheds the water away, and here on the inside they put insulation, flocking insulation, which this then also protected from water by shedding it away. On the inside of that wall you kind of get the exact opposite expression than on the outside. You have this very subtle play of the modification of these slats, so they build little waves, and they use these kind of two sides of the same coin approach to give it a specific architectural expression that is absolutely rooted in the fabrication process. As a conclusion, this project is kind of a negotiation between the design intent, the process, and the performance requirements. And the scripted design system allowed the students to have a playful back and forth between the design and the process. With that, I want to move to the next project, which was a research project at ETH Zurich. The project leader was actually my office partner, Michael Knaus. It was a small pavilion for the opening of a new highway near Zurich, and it had to incorporate a bar in the center. So here you had a bar, and since it was only for the opening, it was a temporary structure. It was 8 by 8 by 4 meters. In floor plan, it looks like that. And the next important aspect here is that there were process requirements from the fabrication process. There were structural requirements to fulfill. There were environmental conditions to address. And the most important aspect, this is the first time that there was a programmatic, an architectural programmatic approach that required certain spatial conditions to be fulfilled. In a pavilion structure, in a very limited scope, but still you needed to provide enough space around here, you needed to provide enough head space, and then combine that with the actual fabrication process. So before we get to the result, I want to briefly give you a few ideas of what we were dealing with in that project. One of the important aspects were wind loads, which might sound boring at first place, but through the wind loads we had to address the connection technique between the slats. So we were using nailing in the last project, but nails cannot take tractive forces. So when you have wind loads, you get a lot of tractive forces here in these edges, so these edges are pulled just apart when stronger wind load happens. So we were switching to screwing, because with screws you can then take the tractive forces, but then you have the problem that screws can rip out through the wood like that in the corners, and this is why the overlap here in the corners had to be extended. This will be important later on. Another aspect is that the overlaps and the screwing were not enough for the engineer of record who had to sign the whole thing, and he wanted additional kind of pre-tensioning inside the structure. But the pre-tensioning then caused the trouble of bringing down the pre-tensioning loads here in the center. And this led to the development of this overlap here in the center, where the width of the overlap is defined by the force that is happening at the overlap. And since you add more and more weight towards the bottom of the column, which is upside down actually here, this overlap increases towards the bottom of the column. And now an important aspect for the spatial design was the twist of these columns. The twist of the columns really opens up the bar towards the inside. It makes an invitational gesture of the pavilion, and it also opens up the headspace for the people moving towards the bar inside the pavilion. And then this kind of again caused trouble with the engineer of record, who said this twist will weaken the structure. And we then were able, by integrating into the design script, because this was again scripted, these column structures, we integrated very, very simple graphic static calculations. So we were able to show that the forces in each of these connections are actually the same for a twisting column than for a straight, or than for only a bending column. And this was important because in normal structural calculation software, they don't work with these elements. They just assume 4 solid walls, for example, and that's what they work with, and that's why they need so much bracing and stuff. But you still need these. You still need structural engineers that sign off your projects in the end. And by doing so, we could convince the engineer that with our qualitative, not quantitative calculations, he can be sure that the values are the same for both solutions. And so now I want to come back to why all these technical factors are so important for the design. We're not trying to see these technical factors as limitations that kind of destroy your original design idea, but we try to pull them into the front of the design process, integrate them into the design process, and then make a more interesting architectural result out of them. So for example, we exaggerated the overlap of the slats in the corners. So we did not want to do away with the overlap, but we even increased it in order to show that this is not a surface design, and in order to visually also increase the twisting effect of the columns. The second aspect of this design, so this is the corners. The second important aspect was this load path, bringing down the vertical loads from the pre-tensioning. This was integrated with the lighting concept of the structure, and then became this almost structural ornament here in the center of the column. So we always try to combine architectural aspects with performance requirements and fabrication requirements, and generate an interplay between them in order to achieve a more meaningful result. So as a conclusion from that project, by adapting the fabrication process to work with screws, we were able to open up new design possibilities, so deal with tractive forces, which made this structure at all possible. And the second more important aspect is that designing with and for fabrication and integrating the performance requirements really allowed to open up new design possibilities. They allowed to open up possibilities of which we wouldn't have thought before. So in the first place, these were only surfaces in a Rhino model, which was way less interesting than having these overlaps of the slats and the light shine through the structure. This was kind of all triggered by having these requirements already, or have knowledge about these requirements already in the beginning of the design process. So we hope also that the very close collaboration between architects and an engineer within the process, and the exchange and communication which can be enhanced, for example, by writing your own software, can leverage new potential for the design. And this is an image from the opening with which I want to end kind of the research part of this talk. And we are now slowly nearing more the center of the diagram, where the development, as you already have seen here, of a fabrication process and the design goes more in parallel, more in hand. You start modifying the fabrication, you start adapting the design, and this goes back and forth and back and forth. So this will get me to the first project from our office, Rock. We're actually a very young office. We set up the office 1.5 years ago, or even less, a year ago. And the first project is something we did before the office time. It was a competition for the Arch Plus magazine, which we're lucky to win. And the competition asked for the development of the fabrication process and then designing with this process. And so here we had a perfect back and forth between process and design. I will briefly explain what we used as a process. It is based on a geometric property of unfolding geometry when it has zero Gaussian curvature. So this is fairly technical, but just think of geometry in the form of cylinders or cones, which you can take and fold from a piece of paper. So you can bend a piece of paper into these shapes. And you can also do this with more complex surface arrangements as soon as you pay attention to the fact that all lines going from every point on the surface focus in one point in space. You could also do that via optimization, but we thought taking this property and integrating it with a design tool is more interesting, because then everything we generate is already producible. This is combined with an actual fabrication system. So when you have your surface that you can fold into a flat sheet material, you do not really know how to generate the shape. So these surfaces are perforated in 3 dimensions. Then they're unfolded with a whole perforation pattern. And when you now pull these 2 surfaces together again, you get back to your original shape. So this is shown here. This is an unfolded perforated panel. We then pull these panels together with these strips and spaces in between, and this then gives the shape that was originally developed in the digital model. At first, we intended to use this as a formwork for concrete pouring. I did a first prototype with that, but we soon wanted to explore more interesting applications, because the concrete pouring was kind of limited due to the spacers. So this did not fully make sense. So we looked more into facades, and also then later on I'll show that into structural applications, because we wanted to make a design with it. And this was how the development of this process was informed. We developed 2 systems, a heterogeneous connection system, where the connection is made from an additional part, and a system inherent connection system, where the connection is made from the material itself that we used for bending. I will briefly explain the heterogeneous connections, so for example screws or these strips. And at that point we started a collaboration with facade manufacturer Seele from Germany, and they started to support this research. So they were providing us with machines and also knowledge about the facade building. So we did a first prototype with this heterogeneous connections, where the important parameters were the bending radii limits that such metal panels impose, and the construction limitations that are just the time that it requires to pull together these panels. To give you an idea how these panels are generated. No. So we now see everything that we explained, that I explained so far in one video. This is the software tool we developed in Rhino, with which you can generate panels that are always unfoldable. So this is a very simple approach. As I said, you can do that with arbitrary geometrical shapes via optimization, but for that project we like the direct approach. So by clicking your way through space on these extension lines, you ensure the unfoldability. Then the bending radii are analyzed, and we choose this most strongest bending panel for first prototype. Then the tool generates all the machining data, like the hole pattern, and also the screws for it, everything necessary to fabricate it, and then it unfolds it into a flat panel, which you can see here on the left-hand side, generates the hole pattern, and this is then given to Seele for manufacturing. At that time, we had a lot of time, so we also developed tools to really bring together these metal pieces, because it's not so trivial anymore to bend a 2mm stainless steel plate. So we developed our own physical tools to do that. And with that, we were able to make a first prototype. This you will see here in a... So this was the piece for the first prototype, where also the overlaps are an important factor in order to ensure curvature continuity of the facade panels. Why Seele was so interested in the process is that bending very thin sheet material stiffens the sheet material in itself, and by that, with thinner material, you can cope with higher wind loads on facades. So here you see the construction of this first panel, which is still quite work intensive, so this is something probably to automate. And the first prototype used screws sticking through the material, but then we switched back to bolts, which allows us to give a really seamless surface for an outer facade panel. But as I mentioned, this was the one connection type, and then we looked also into a system inherent connection, which you can see here. I don't want to go into detail about that. It's just connecting the two panels with the same material. And this was the basis for the next important step, which is a load-bearing connection. We set up a collaboration with ILEC. This is the Structural Engineering Institute where Frei Otto formerly worked, which is now led by Sobek engineers in Stuttgart. And with them, we wanted to research how these panels could perform structurally. So the first thing to research was the orientation of the clips. So you can bend these panels in the same direction, but connect them either towards the inside of the curvature or towards the outside of the curvature. And this was a test suggested by the engineers, and then we did these test probes, and it clearly showed that there's a huge difference. So the blue one performs a lot better, which you can see here, where the clips are bent towards the inside of the curvature. The second important aspect was the orientation of the clips. So not only the side towards the curvature, this is relevant for compression or tension stresses within the material, but also the orientation of the clip in the surface normal direction. This is important for the main stress axes. So this is what is analyzed for this panel with these connection points, and then a force from the side. You get these bending moment distributions, and you get these main stress axes distributions. And by orienting the clips towards what you can see here, or against the main stress axes, you can further stiffen the panel. So the orientation is based on the compression or tension, and the orientation or the rotation is based on the main stress axis. And this formed the basis for our design development of a pavilion, because the final hand-in for the competition needed to be an architectural structure developed with your process. And for the development of the design, then we looked into existing structures that operate with cylinders and cones or combinations of both. And traditional vaulting structures generate very sophisticated results with this approach. In an abstract way, this is what you can see here. All cones and cylinders have zero Gaussian curvature. And when you intersect them in certain ways, you can generate very interesting vaulting results. We combined that with the analysis of the structure in order to decide where the clips have to go. So we compare the cone generated form, which is this line you can see here, as in a section of the panel, with the ideal catenary shape. The catenary shape would give you only compression forces inside the structure, but we cannot do that because then we could not produce the panels anymore. So this is how we were able to determine where we have compression and where we have tension in the structure, and place the holes accordingly. So we did not have to have any complex static analysis, but could do that with very simple means. And this will demonstrate the design system that we set up to make our final pavilion. So here you can see these diagrams with which we could move the points around, and then the structures adjust to it. So within this system, every solution is a buildable and structural feasible solution. So we could now start developing our designs through that. And there is now again a huge range of possible design variations. So this was this analysis I talked just a slide ago. Here you can see different approaches. So it is possible to move the base of these columns. It is possible to move the upper corners. It is possible to move the outside corners. And we choose a fairly complex site where we have height differences, and also connecting to existing buildings, so that we could really demonstrate the potential of the fabrication system, the design system we developed. So this is a very systematic approach to architecture, but then again we use it to generate interesting architectural effects. So for example, the light patterns that emerge from the clip placement on the floor, or the clip placement patterns themselves, this is the top roof view, are the design expressions that are generated by this process development. So we again try to not kind of push through a design idea initially conceived, but play with the development of the process in order to make an architectural design. This is a model we built in the end. And this is almost now at the center of this diagram, where the architectural design development and the process development went hand in hand. And the next project, there they become really the same. So the architectural concept and also the fabrication process are really the same thing. And this is a very rare kind of happening, I would say, and it's probably only possible in a certain scale or scope of projects. So it was an installation for a gallery in Basel, where we were asked to do something with the interstitial window space. So they had a kind of 1 or 1.5 meter deep shop window for which we should make an installation. The kind of design idea, an architectural design concept, was a play with the title of the lecture series this gallery is hosting. This lecture series is called Standpunkte in German, which in English is point of view. So we started to work with that idea of the central perspective, and used the storefront kind of as the projection plane for the focal point. So point of view or focal point was the architectural concept, and this is a top view, and here you have the sidewalk. And within one point at the sidewalk, we focus all of the kinks and all of the lines inside the structure. And by doing so, when you walk into this focal point, the structure or the installation completely dissolves. So you only see the kind of the front sides, and you get a clear view into the gallery space. And when you then gradually move away out of that point, the installation starts closing off the view inside the gallery. And when you're looking at it from the side, it appears as a completely solid installation. We were also looking very much into the fabrication of this structure. Then to really get this idea to work perfectly, we needed a thin material being connected as little as possible, so that when you're in the focal point, you get a clear view and are not obstructed by any connection or construction techniques. We also, in that case, then used this focal point idea for the fabrication, because when we focus all lines, we can do the same thing again. We can unfold these panels and then fabricate them very easily from flat sheet material with a standard kind of cutting knife. Machine available to us at ETH, so this project was supported by the Rapid Prototyping Laboratory there. They allowed us to use the machine for free, which was very generous, because these small projects, they don't have a budget. So you basically get paid for the material and a little bit extra, and then you have to see how you make something interesting out of it. And this also then plays these limitations of budgets, this plays into the connection system. We used simple paper clips then to connect the folded strips at this one single overlap. And by doing so, we were able to work within these very limited budget constraints. On the inside, you get kind of the opposite effect. You get a light effect, a light gradient towards the focal point. You look always towards that point on the sidewalk. Although the structure seems to be pretty solid, it transmits still a lot of light into the gallery space. So as I mentioned, it's a very rare situation that you can really combine the architectural concept with the fabrication concept. But in our sense, this is kind of the ideal world. But it probably is very difficult to do so in larger scale projects. With that, I want to go to a very short next project. It was a laboratory space for a structural engineering professorship at ETH. Where we again had to work in a very limited budget and very limited time constraints. It is not only the laboratory space within a larger testing facility, but also an exhibition space. So the whole structure was conceived as basically one huge shelf, which has openings in certain parts. So here you can see the shelving structure, which is the structure itself, and then showing the models in certain spaces. What we did here in order to deal with these very limited constraints but still make an interesting result, we implemented, because we knew about the whole fabrication process. There was a carpentry available to us who had a setup procedure to make these shelves, but then we didn't know how much, because glass costs more than the enclosed facade, and so on. And we input these parameters into a simple Excel spreadsheet that was connected to the geometric model, and then we could modify the amount of openings, the placement of openings, and immediately see what that would mean for the timing and for the budget. So we tweaked that to gain a maximum of opening, because we want to exhibit as many models as possible, and also to limit the timing for the construction. So it was possible through the whole prefabrication chain that followed this design to build it up within 1 week, and this was also another constraint that we had to work within. And we could already see that while designing inside the Excel spreadsheet, and that was the important fact, because otherwise we probably would have lost a lot of the openings that we now have. And it's still not many, but at least a few. So the next project is, I can only show it digital because unfortunately it's not built yet. The client, I've still undisclosed, but the client actually is Holzer Kopler Architekturen from Zurich, which are building an exhibition space or an installation for an exhibition. Which is made from the Bayern and Faela foam, the same thing that has been used for the water cube, for example. And it is an exhibition for old artifacts, and they should be placed now in these cell clusters. And this is not the actual design. This is only a test model from us. We cannot show the actual design, unfortunately. And the difficulty here now, and this was when they approached us, the difficulty here is that you have this foam now, you like the idea of the foam, but you are not able to adapt the shape of this foam-like structure to your actual exhibition needs, because you probably want to have a very large cell here, a very small one over here. You want to have the one cell planar, the next one with a tilted space. So it's now possible to do that. You can start editing this model. You can pull corner points around. But when you do that with polygons, you suddenly run into the problem of getting bent panels everywhere. And when you have a bent panel, again, you cannot fabricate it. I'll probably show this project best in a short video. So when you have triangles, it's easy to pull around points in space, modify them. This is what we do here, and still keep the panels flat, because obviously triangles are always flat. So when you look at the curvature, which gives information about the bending of a panel, when you look at the curvature, these triangles are always flat, no matter how much you modify them. When you do that with polygons, as in the foam, where you have several corner points of the plates, and you modify pulling them around in space, you get bending all over the place. So when you look at the curvature of these modified polygons, then you will see here now that there's curvature. So these are the red areas. This is where the panel is bending. And you cannot produce that from flat sheet material, so it gets insanely expensive. So our tool now relaxes the structure again, so that all the surfaces become planar again. So when you look at the curvature now, after applying the algorithm that we developed, you have zero curvature again everywhere. And this is, I think, a basic concept we always try to work with. This is the extension of the design system idea, where you make your own tool and you integrate it into your design process. So this is not a black box. You throw something in and it spits something out, but there's an interaction between the designer and the algorithm, going back and forth between design and algorithm. So you make a little modification, you run the algorithm that planarizes your design again, then you make another modification. So there's a kind of playful interaction between the software in the computer and yourself as an architectural designer. So this is demonstrating the same thing, but just with a structure that is more similar to the actual structure. What you can see here, there were constraints applied so that, for example, this bench always stays planar. So when you want to integrate a bench, you can also say always keep the surface horizontal. So there are many things that you can do with this tool to also analyze your results. So for example, you can look at the edge lengths, because when this will probably be manufactured from wood panels that are cut with a mill, and when you look at the edge lengths, too small panels just cannot be fabricated because it's not possible with a machine. So we integrated all these later on constructive constraints into the tool and made them available right in the beginning of the design process to the architects. And by making them available inside the software, the architects could really play with these constraints, and again, not optimize them afterwards and get a result that is differently to the architectural intentions, but have a back and forth between architectural intention and optimization routine. And now we gradually move more towards the right-hand side of the diagram, which a project follows that we actually did for Jean-Lucien's office now, who was collaborating on the competition with DGJ. And here we entered the project after they won the competition, and were responsible for the translation of the images applied to the interior facade into kind of a materialized detailing system. So we had rather limited design freedom. We only had freedom to develop the detailing system, not the design. So this is kind of the last step where we were still involved in a very tiny part of design decisions. So we proposed many different approaches of how you could materialize the images, like for example cutting wood slats that are normal to the facade surface by thus showing the images on the facades. Actually, these images are persons that lived in the area around the bank, and then this was another system that we proposed, which is just simple cutting holes into panels. And this was then the one they selected. And we made kind of many variations of that, whole plethora of more complex or less complex arrangements, testing when do you still see the facial patterns, when do you not see them anymore. This was kind of a play with abstraction and less abstraction. And then we soon tried to also think about the materialization of that, how you could play with the detailing. So for example, do we use angles for the corners? How does that affect the lighting from the back of the structure? how does it affect the shadow play. And for that it was crucial that we did early prototypes, and DGJ now had a good contractor they were used to work with, and this contractor already very early in the process in the design process allowed to do tests. And these tests were not only for the detailing crucial, but also for the resolution of these panels. We did a few test panels in wood, for example, where we were testing out different sizes, which was relevant for the visibility of the faces. So it was important to test this play between, as I mentioned, abstraction, which you can see here when you get closer to the structure. It becomes more an abstract pattern. The further you're away, the more strongly you see the faces. And this was only possible to test in one-to-one scale. That's impossible to see in a model. If you see it on a computer screen, the smaller the screen, the more visual the faces. And thus you really need to see it from a one-to-one distance with a one-to-one size with a one-to-one detailing. There's no computerized abstraction possible. A nice story is that when you're in the bank and take a snapshot with your cell phone, on the cell phone the faces look like printed, although when you're close to the panel you might not even see them that clearly. So this is a nice interplay that we were looking at while developing this detailing system. So the last project, which is now at the right-hand side of the diagram that I want to show, is a pure kind of optimization project where we came in after all the design was finished. It was finished a long time ago. It's a purely consulting project, and this is basically what you get a lot in the current building industry. And this is in strong contrast to the project we did with Jean Lucien, who brought us into the project very early, basically, and which makes the project much more interesting then. In that project, we come in basically as in the end to kind of rescue the fabricatability of the project. So the project is the Stuttgart 21 main station. It is a project initially developed in collaboration between Frei Otto and Ingenhofen Architects. Frei Otto developed the structural soap film analyses for these columns of the station. You can see these eyes of the columns up here, which are these eyes over here. And this is the interior space of the station. And over the years, the project has been modified a lot, and also the engineers changed. Frei Otto, unfortunately, is not anymore in the project team. He's opposing the project now. The engineers of record are now SOBEC engineers, and we have been commissioned by them to do the reinforcement planning for this project. So this is pretty dry technical stuff now. But it also taught us a lot about actual building processes and the real-world conditions you're actually working in. And we, as an office, we were responsible for 4 parts of the whole project. So this was the generation of the reinforcement. This was the geometry management. So we managed the whole geometry of this reinforcement model. Then we optimized it, we rationalized it for construction, and we did the quality control in the end. What this all means, I'll briefly explain in the following slides. So the generation of the reinforcement is based on very simple input geometry. This is basically the form that Ingenhofen Architects shaped in MicroStation. Then we get this shape from the engineer SOBEC, and we get a huge pile of rules how the reinforcement has to be laid out inside the structure so that all the structural criterions are fulfilled. To give you an idea about the scope of the project, I'll show a short video which shows the generation of the reinforcement for one of these columns. So inside one of these columns we have around 28,000 reinforcement elements. So this is the generation of these reinforcement elements based on the input geometry and the rules by the engineers. There are many different areas where different types of generations then are required. So for example, building facing, you can see here, so there is a face in the construction process that stops here and continues above here. There are special elements like clips and at ending conditions. There are very high curvature areas, also very low curvature areas. All these different types of geometries require different approaches for generating the reinforcement. In the end, what had to be produced are reinforcement layout plans. This is what you can see here. This is actually what the workers on site then use to place the geometry, to place the reinforcements into the formwork. This has not been prefabricated, but this will be fabricated on site. And this is what gets us. No, I'll talk about that later. The second aspect of our work was managing this huge amount of data. You have 28,000 bars per element. Then you have to apply this to all types of different elements. All these columns are different. They look the same, but the station has a roof inclination, so these columns are all different. Then you have all types of different parts, special parts. And the nice thing now is that we don't develop a parametric model, because a parametric model would be only applicable to one specific geometry, which basically has always the same topology. So you could not apply a parametric model from this surface to that surface. This would just fail. But with the algorithmic approach that we are taking, it is possible to transfer the algorithms, sometimes with very minor modifications, from one totally different piece of geometry to another piece of geometry. Parametric models prohibit that, because you build up a parametric model like a tree. So you have a basis and you build your stuff from that basis onwards. And now when you exchange the basis, your model usually doesn't work anymore. But if you only work with parameters in an algorithm, you can adjust it. That's why we are also supporting algorithmic approaches, at least in that type of work, over parametric modeling, which can be very useful in other aspects of a design or a construction process. The third part of our work was optimization. So many of these bars were, when they're first generated, they're wildly bending in space. They're bending in all directions. And as you can imagine, a bar bending wildly in space is pretty tough to fabricate, because you have no point of reference on how to make that. You can basically only make it with very expensive machines. But the actual process of bending rebar is a very manual one. It's bent over the knee or with a very simple machine in a plane. And they get a drawing in 1-to-1. They put on the floor, they bend the bar, they put it on the drawing, and they see how the bar fits the drawing. So it can actually be, such a thing can actually become a constraint. And so you're starting to optimize for such constraints. For example, I only show a few of the optimization steps. One optimization step is make as many bars as possible planar. There were around 60% multi-curvature or double curvature bars, and we got it down to 5%. So this was a huge lowering of the cost. With 60% double curvature bars, the project would have been impossible to make just due to cost limitations. So the second optimization, for example, is simplification into arches. Then we had a whole set of tolerance rules. So some bars, for example, don't need bending at all, because they would lower themselves into place. So you try to, within the tolerances, you try to take these bars out of the whole bent batch of bars. And as one of the last steps then for us was the rationalization of the geometry. Again, with these many elements, it is very difficult later on for construction logistics. So when you go on site, you have, I don't know actually the actual number, but they have more than 40 manufacturers making these bars. And then this building is constructed over a time period, I think, of 6 to 7 years. So these need to be delivered at the right point in time to the right location with the right bending radii and so on. So you somehow need to group these bars into construction facing and also into similar types of geometry, because one manufacturer is best only doing one type of curvature. So again, with intolerances that were allowed to us from the engineers, we're trying to group as many bars, make as many bars as similar or the same as possible. So all the same colors here, so all green bars, they're widely distributed through the whole thing, but all the green bars have the same curvature and also the same length with intolerances. And this will facilitate then the building logistics later on. And the last step, what we were responsible for, was the quality control. So we had all these rules from the engineer, which was almost a small folder full of rules. And how do we ensure that we don't make a mistake? Because insurance for such a project you cannot pay for, so you better make no mistakes. And this is why we also took over our own quality control, and the quality control in that case for the engineers. And this has been done by having one person work on the generation and optimization, and another person completely independently work on the control of the rules. So both got the same batch of rules. The one writes checks, the other one writes the generation. And then these checking rules are going through the geometry that has been generated and are controlling if everything is according to rules. So this is what you can see here. These dots then show if the results fit the rules. So where you can have red dots, these are areas where you better look into and evaluate them visually. Because sometimes, for example, we are outside what is allowed with intolerances, but then the engineers have a closer look at that area and they say, it's okay, and never mind in that area, because in that area the forces are anyway not so strong in that direction, whatever. This is a part we don't know, but then you have a tool to evaluate the results. And again, I want to end now this talk with this last slide and again mention why we think that algorithmic approaches are so important, because at the one hand side, as towards the beginning of the talk, they allow you to rapidly adapt to different design approaches. They allow you to rapidly adapt to different fabrication processes. You can jump back and forth very quickly without changing complex models, without changing complex arrangements of geometry. And the other important aspect for the consulting work is that they allow you to generate the results again and again very quickly with different types of input. So you, for example, this is one sheet of the rules we get from the engineers. They were usually sketches like that. So at the one day you get a sketch that looks like that, and the next day you get a sketch that looks completely differently. But then you have all the set of your rules. You have your pretty complex algorithm program running. You adjust these rules, and then it's possible to do these things. And because the checks are also running, so the quality control is also running automatically. And with that, you can be sure that the results you produce are correct. So with that, we're able to do that. At 8:30, this email arrived, and they asked if we can do it in the same night. And we usually did it, because this was crucial for this very close collaboration with the engineers, which was important for the project to succeed. So with that, I would like to end the talk, and thank you for the attention, and again, thanks for having me over here.
I mean, looking at your work, it seems like there's way more than architectural design. I mean, there's a lot of scripting and engineering. But you came out from architecture school, so I wonder where all that knowledge about scripting and engineering that I don't know, I don't think we have in English. I don't know if you get it from ETH, but where is all the knowledge that you get from these two big fields?
Yeah, well, basically the brick wall project that I showed, that was well, one project, one design studio I did before but there we did it on our own. But the brick wall project was what sparked the interest in such technologies. But then there is not much more offered. It's basically teaching it to yourself.
It's like doing, right?
Yeah, we're kind of technology fetishized. So we really love that, and yeah, we develop that skill set by doing projects in university, but then also after university. Like the Arch Plus competition, that was when we were working as research assistants, which gave us the time to do such explorations. And but I think it's not too difficult, to be honest. It has a very steep learning curve. You just need to get started. But if you started it at one point and you're enthusiastic about it, I think everybody can learn it, because programming today is not so difficult anymore. It's not like in former days when you had to deal with all the details of a computer in order to do programming. You basically open Rhino and then you have a lot of different technologies available to you with which you can do that. You can use scripting, which is very simple, very good for beginners, but you can also go deeper and develop plugins for Rhino and so on. So there's no limitation to the level of complexity and ease of learning. Yeah.
And you're showing some kind of connection between structural analysis models and scripting.
Yeah.
Scripts. What you see there, is there really kind of a way to automate certain things and to integrate kind of structural analysis model in the script and automate the things?
Well, there is a lot of structural engineers did research or are doing research into that direction. So when you do that, let's say, with a certain depth, then these algorithms become very sophisticated algorithms. There are tools like BSO or ESO that have been already developed like 20 years ago, these algorithms. They can be rather applied only today because they are so computationally intensive. But I think these are not algorithms that are important for architectural design. When we integrate structural analysis, this is not to resolve the kind of final structural engineering analysis with which the engineer then can sign off the project, but it's a way to gain an understanding as an architect of the structural behavior of your system. So it's as I said, it's a qualitative measurement, not a quantitative. You don't get a number that tells you this structure will work in the end, but you get a number, this structure is better than the other one you're designing. This option is better than the other option. And we think during the design process that is the relevant criterion. You don't need to know about the numbers, because to set up a correct FE analysis, how an engineer would do it, is way too complex for an architect to do in the design process, and is beyond our level of knowledge. So that's why we don't use FE analysis, but we use graphical statics, which are very intuitive to grasp. So maybe you've heard of the Cremona plan in your studies. Things like that are graphical studies in 2D, but you can also do that in 3 dimensions with computation. Mm-hmm. Then you have equation systems to solve, basically. That's and that will give you the solution for your structural question. But I would say it's the qualitative result is important only for architecture. It's not the number.
And how you see it in the future now? We're looking at the robots and in terms of prefabrication, automatization, a lot of processes. And so do you see that more kind of as more and more prefabrication? So will you really work on the parts, or do you see really kind of for example, robots working really on the construction side and really doing things on site? Or what's your vision there?
I mean, it's difficult to define a vision, because there have so many visions been defined in that field of work. So Greg Lynn was already 95 arguing that there's a whole shift in architecture happening with new fabrication processes. At that time it was the mill, now it is the robot. I mean, these tools, as I said, are interchangeable, I would say. I think it's more important that you develop a clear approach towards such projects. So when you want to implement technologies into the design, it's easy to forget the user, it's easy to forget about the client and so on. That's what we are learning currently with our current projects I didn't show yet. It's more important to develop a clear approach that you have, for example, when you get a new project, you quickly define what are the technologies available to me, how do they relate to the task, how do they relate to the final result, how do they relate to the user and what he gains from it. So what is really the advantage? So not only applying the technologies for the sake of the technology, which is easily done and with a fascination for technology is also quickly done, but then have one step back and rethink why you do that. I think that's the important part. I think the machines themselves are
more about the scripting and programming than the machine itself.
That definitely. I mean, it's more about an approach. You need to go out. You need to know what technologies are available at what price. For example, for actual projects, the price is always important. So you need to talk to people. I think it's also communication that is very important. You need to convince, for example, people that you're allowed to use their machines for testing. That was something that was not so trivial in the beginning of the Raiffeisenbank project with them. They are very reluctant to let, and at that time even we were only allowed to give them geometry, but we could have delivered G-code, but they're afraid to do that because you can destroy their machines with what you do. So you need to set up collaborations with manufacturers. I think all these kind of soft factors for a practice are much more important, because in academia you can easily do all these things directly. You have a robot, you have the greatest tools, you have digital cutters and so on, but that translates very badly into real world. I think this is why we are currently at a kind of critical stage where you have all these pavilions popping up at all the architectural schools that have these technologies, but they always stay pavilions. They never become architecture where you deal with program. They never become architecture where you deal with more complex conditions like just a building enclosure and things like that. We try to address very specific aspects of that in the teaching, for example, with the exterior wood wall, but it's always only a cutout of a larger thing. And this is probably the most critical development at the moment. How do we move one step further and applying these approaches then really in larger scale projects, in architectural projects, and not only for pavilions. I think that's what your generation and maybe our generation, the challenge is up to do. Yeah.
Okay, then thank you very much again. Thank you very much also to the Student Association and to Francesco Oesterle that organized that, and I think they organized a quick
Okay, we have it here.
Okay, we have it here. Thank you.
Great.